Hello and welcome to this video. This is the fifth video in the series of videos for module on electrostatics, which is part of class 12 physics. The last video we saw the idea of flux and the Gauss law associated with that idea, and in this video we shall see some applications of the Gauss's law. First of all, I said already that Gauss law is always true, always correct. However, it's not always useful actually. If we want to apply Gauss law in order to obtain the electric field for some charge configurations, then the charge distribution should have certain degrees of symmetry actually. Without the idea of symmetry, without the without being symmetrical, it is not easy, or in fact not going to be useful at all to utilize the Gauss law in order to determine the electric field. However, we shall start with a very interesting result, or actually at least a result which is seemingly not very clear at the first sight actually. This is known as the Earnshaw's theorem. Okay, that's the first application that we see. What the result or what the statement says in this case is that if I have a system of charged particles, static charged particles, then these charged bodies, they can't keep another charged particle in the state of stable equilibrium only by acting among themselves. So if the electrostatic forces are the only forces, then we can't have stable equilibrium of a charged particle actually. Now, how does this come out to be? We see that there are some situations where seemingly the charged particle is at equilibrium. For example, if I consider 2-point charges which are kept at the end of a, if we just keep 2-point charges at two fixed points, say for example these are both identical, plus q and plus q, we notice that if I put a third charge in between them at the midpoint, this third charge is going to be at equilibrium because this is equally repelled by this charge q and this charge plus q. We find in this case that this plus q over here repels the middle charge in this direction towards the right. On the other hand, the charge which is this one is going to repel it in this direction, and because the forces are identical, because the charges are identical and the distances are the same as well, as a result of which the middle charge is in the state of equilibrium. So at least the equilibrium condition is there. But is this equilibrium stable? Now you must be knowing that when I say, or when we want to show that an equilibrium is a stable equilibrium, what we need to do is we need to disturb the charge or the system slightly and try to see whether or not it has a tendency to come back to its original equilibrium. So when I disturb the system from its equilibrium position, restoring forces should arise, and these forces should try to bring the system back to its initial configuration. Now in this case, if I displace the middle charge, which is plus q, this middle one, if I displace it slightly in this direction, for example, suppose I just take this charge over here. Now I see that because it has gone nearer to this charge over there, as a result of which the repulsion of this charge on capital Q increases, and the repulsion of this plus q on the left side over there it reduces slightly because the charge has gone a bit away, which means therefore that in this case, if I look at the net force acting on the middle charge, it is towards the left, which is actually trying to bring it back to its original configuration. So it seems stable basically. However, what happens, for example, when I disturb the middle charge not along this line but perpendicular to this line? For instance, if I displace this point charge q slightly above on this side, so it comes over here now. Now I find in this case that this left side charge is going to repel that one in this direction, and this right side one is going to repel it in this direction, and these two forces being exactly the same, the resultant of these two forces now is actually this way, which is going to take this charge away from here, never to come back, which implies it is not stable in this direction. In fact, we see that this middle charge q, apart from the displacement in the along this line, in any other direction, if I displace it this way or this way or this way or this way, it is not going to come back. Fine. This particular kind of equilibrium, in fact, they refer to the saddle point equilibrium. They are like, the saddle of a horse, where we just put something on the back of the horse, which is called a saddle. So find in this case that this is the shape approximately. So if I have an object over here, a small ball for example, if I disturb it in this direction, it will come back to its position, but if I displace it in the direction which is this way, it will, or any other direction actually, it will simply go away, never to come back. Okay. So that means in this case therefore that the equilibrium is not exactly stable, because had it been in stable equilibrium, doesn't matter in which direction I displace it, it should come back. Fine. That is what the meaning of stable equilibrium is actually. Now, how does this Gauss theorem helps in proving that we can't have point charges at static equilibrium only, under the influence of static point charges? How does it turns out that a body cannot be in stable equilibrium? So the idea is this. Say for example that we have a positive point charge over here. I'm assuming this is positive, and there is electric field around it in space. There is some electric field around it. Now, if we want that this should be a stable equilibrium, then what should happen is, if I displace it from this position, say for example I displace it in this direction, then restoring forces should arise, which should bring it back. But then this is a positive q charge, which implies if it's experiencing a force in this direction, there must be an electric field into this point charge. Obviously it's not of this plus q, but some other charges. Fine. The same argument applies in all directions around this plus q. So if this plus q was in the state of a stable equilibrium, then irrespective in which direction I displace it, it should return back to its original position, which means that it should experience an electrical force inwards always. So that implies that around the space of this charge, the electric field should point inwards. As I said, this electric field is not due to this point charge, but some other charges. So this should be there for the way the electric field should be arranged around this charge q. But that means what? If I consider a Gaussian surface which is going to surround this point charge q over there, these are Gaussian surface which is surrounding this charge. So the fact is, if I compute the flux through this Gaussian surface, then I find that the flux is positive. The flux through this surface, is negative. Why it's negative? Well, the reason is simple, because at every point of the surface, the electric field is actually pointing inwards. And we know that for a closed Gaussian surface, or for a closed surface, if I wish to obtain the flux, I should take the area vector pointing radially outwards. So the electric field is pointing inwards, the area vector is pointing outwards, and therefore the flux is negative. However, according to the Gauss's law, what I know is that if I compute the flux of the electric field over any surface, this should be actually equal to the charge enclosed by epsilon 0. Now we have already seen that the flux is negative, so the left hand side over here is in fact negative. But if I look at the right side, the Q enclosed, that is in fact positive. I already started with that one. But this is a contradiction actually. We are getting therefore that a negative number is equal to positive number. That's not going to happen. So we have got in this case a contradiction, and that means therefore that this cannot happen, which implies that at all points around this point charge Q, the electric field can't be inwards over there. The same argument will work even if I take the point charge to be negative, because when we have a negative point charge and I displace it, then it should experience a force inwards as well, but that means the electric field must be outwards everywhere around it. Fine. And that should mean the flux is positive, but the charge enclosed is negative, so we again have a contradiction. Okay, so that is basically proving this Earnshaw's theorem. As we shall see later on, this will be also true in case of magnetostatic field actually. So the idea is that with only static fields, a point charge cannot be kept at the state of a stable equilibrium. It can be at equilibrium, but it won't be stable actually. Fine. Right. So next we actually go into the application of the Gauss law for finding the electric field actually. Now if we wish, as I said already, if we wish to find out the electric field due to a charge distribution using the Gauss law, then some degree of symmetry is required. Fine. Now as far as we are concerned, there are not many kinds of symmetry we will be dealing with. There are only three kinds of symmetry where Gauss's law can be used to give the electric field easily. Fine. The first one is called a spherical symmetry. In a spherical symmetry, what happens is the entire properties, all the properties over there, including the charge density or the electric field, it will depend only on the distance from a fixed point. That point will be the center of the entire charge configuration as well. Now in this case, as a Gaussian surface, we shall take up a concentric spherical shell, a spherical shell which is centered at the center of the entire charge configuration as well. Fine. The second kind of symmetry that we have is a cylindrical symmetry. Now in this case, the charge density depends only on a distance from a fixed line. This line will be nothing but the axis of the cylinder we will be dealing with. And in this case, as a Gaussian surface, we shall take a coaxial cylindrical shell. So we have to take a cylindrical shell, and this should have the same axis as the charge configuration. Okay. And finally, the third kind of symmetry that we have is a planar symmetry. In a planar symmetry, the charge density depends only on a distance from a fixed plane. Fine. And in this case, as a Gaussian surface, we shall take a pillbox or a cylinder which straddles the charge distribution. What it means, straddling is something like that. If I consider, for example, a surface which is imagine that we have a very large surface like this which is charged. Then when I say straddling, it implies this is like we can take a cuboidal box or a cylinder as well, doesn't matter. So for example, if I take up a cylinder, that cylinder should kind of go this way and the other way around as well. It should be having a kind of straddling implies something like this. So this cylinder is therefore basically cutting it. Some part is on this side and some part is on the other side. That is what is straddling means in this case. It's just going to be intersecting it in a transverse manner, right? So these are the cases that we will be dealing with. We start with the spherical symmetry. As I said, in case of a spherical symmetry, the distribution of the charges will be dependent only on a distance from a fixed point. Now the special case, obviously you can have a point charge as an example, by the way. Doing it for a point charge is rather straightforward. We just take it up for a uniformly charged spherical shell. So a shell is like an envelope, spherical envelope. We assume that the radius of this spherical envelope is, say for example, capital R. It is charged only on the surface. So the charge resides on the outer surface over here, and we're going to assume that the density of charge, in this case it is a surface density, implies the charge per unit of area, that I'm going to take as sigma. So sigma in this case is the charge density. Fine. Now first of all, before we deal with the finding the electric field, we need to argue a bit over there. We notice in this case, because of the spherical symmetry that we have over here, the electric field cannot have any other component apart from the radial component. Fine. Because that is the only unique direction over there. I mean, had the electric field has some other components, then I'll be able to, for example, it has a component, suppose that which is kind of tangential actually. Then I can just turn the sphere around when you're not looking at it, and when you come back and you look at it, because the direction of the tangent will be different at a certain point, which implies you'll be able to distinguish that okay, the sphere has been turned in fact. However, the point of a symmetrical object is that it will be difficult to distinguish if we turn it around the line of symmetry over there. In this case, we have a uniform, if we have a uniform sphere, it will be symmetrical about any amount of rotation, about any diameter actually. Fine. So it should not be possible to tell us that we have turned it effectively. So that implies that can only happen if the electric field has an entirely radial component, because if it's a radial, then radial at a point, if I am just turning the sphere, then what will happen is one radius will be replaced by the other radius. It will be remaining undistinguishable actually, indistinguishable basically. So we cannot tell the difference, and that is why the electric field needs to have only a radial component. Okay. Now if I consider with that thing in mind, if I take up a very small, I mean as a Gaussian surface, I said I'll take up a spherical surface. So this spherical surface, suppose for example I'm going to take the Gaussian surface inside, I'll look at first inside points where I'm looking at finding the electric field. Now at whatever distance from the center I need the electric field, we shall construct a Gaussian surface which has exactly the same radius r that I'm looking at. This is where I'm looking for the field. At any point on this radius, it will be same because it has spherical symmetry. So as long as we stay at the same distance small r from the center, I'm going to get the same electric field. Well, direction will be different, it will be radially outward at every point, but at least the magnitude will be same over there. So this is our Gaussian surface in this case, where I'm going to calculate the flux. Now for all cases of spherical symmetry, if I look at the left hand side over there, integral of E dot dA, the first thing I notice over here is that for a case of spherical surface, what will happen is if I take up a patch over here which is on the surface of a sphere centered at some point over there, then what will happen is the electric field and the area vector, they will be both in the same direction or anti-parallel, it will be opposite direction. That's what. If the electric field is outward, I mean area vector is always outward, the electric field may be outward, may be inward, depending whether the charge is positive or negative. But in any case, this dot product E dot dA, I could always write on this one as the integral of the radial field into dA, because the angle between the two vectors is either 0 degree or 180 degree. So I'm going to take as ER. ER in this case is the radial component of the electric field. So if this field is pointing outward, I will take it to be a positive ER. If it's inward, it's a negative ER. So okay, in this case we won't have the dot product because not a vector, because this is now a scalar number I have written. There is no dot in this case now. I have simply replaced it with a scalar product over there because we have taken the direction, the product into account actually. Now we again employ the symmetry. The fact is that this radial field has the same magnitude as we stay at the same distance small r from the center, because this has spherical symmetry. Therefore, I can pull this ER out of the integration, and as a result of which what we are left is simply this. But this is asking us to actually add, the integral is asking us to add all the little areas dA in magnitudes. But when I add all the areas of those little patches, I end up getting the area of the whole spherical surface, which is nothing but 4 pi into r square. As a result of which, in case of a spherical symmetry, we could always write down the flux, the left hand side of the Gauss theorem, as ER, the radial component, multiplied by 4 pi r square. Okay. So now we apply, with this thing in mind, this Gauss theorem to the spherical shell. Now in this case, if I take two cases, I'll consider first of all r to be less than capital R. We are inside the shell. If I'm inside the shell, according to the Gauss theorem, what should happen is the flux, which is what we have computed over here, the flux should be equal to Q enclosed upon epsilon 0. However, in this case, there is no charge being enclosed, by the way, and therefore this is actually turning out to be 0. In fact, in this case, Q enclosed is 0. No charge is inside the shell, everything is on the surface actually. Therefore, this turns out to be 0. And that will imply, therefore, that because the flux has an expression of ER into 4 pi r square, this must be 0. Obviously 4 pi r square is not 0. That means therefore the radial component should have been 0. So the radial field has to be 0. Now because there is no other component, it means the entire electric field inside is 0 as well. So the electric field is 0 inside uniformly charged shells. On the other hand, what happens if I consider R to be greater than capital R? Now in this case we are outside the shell actually, but once we are outside, as far as the flux expression is concerned, it is still the same, but this time the charge enclosed, the enclosed charge is nothing but the entire charge. In terms of sigma, if I wish to write down, it will become sigma, which is the charge point of area multiplied by the total area, which is 4 pi capital R square, which is the sphere of the radius of the sphere actually, and we divide this by epsilon naught. So once again, if I replace the expression for phi, what I end up getting over here is ER, the radial field, into 4 pi r square. But this time this r is the variable r because we are looking at outside points, and this should be equal to sigma into 4 pi capital R square upon epsilon naught. So 4 pi gets cancelled out and we end up getting the radial electric field as sigma by epsilon 0 into r square upon small r square. In terms of the total charge, if I wanted to look at that, then we already noticed this is the total amount of charge in fact. So we could have written down this one as capital Q, which is by 4, let's take the total charge as small q. So in terms of this total charge, we shall be able to write down the charge Q by 4 pi epsilon 0 into r square, which is in fact the electric field of a point charge, which means therefore that if I look at the shell from outside the shell, it will simply look like a point charge as far as the field is concerned. But for inside, points it is equal to 0. Okay, that is the shell theorem, and it's useful to notice that the electric field variation for this situation is the radial field I'm talking about. If I'm inside the shell, the electric field is simply 0, but just when I reach the surface, it suddenly jumps to a certain value, which is nothing but sigma by epsilon 0, that you could see when I use small r equal to capital R, basically the limit of the electric field from outside point actually. So it just jumps to a certain value when we reach the surface, and it simply falls as 1 by r square. This is the electric field due to a uniformly charged shell. Now, next we consider what happens when the charge is not only on the surface but also within. So what I have in this case is a solid sphere, a sphere which has been charged throughout the interior. So the entire charge is distributed over here, all over the inside interior, right? So this is, we have a solid sphere over there, and I'm interested in finding out the electric field for points which are inside as well as outside the shell, the sphere, sorry. As usual, we shall be using the fact that for the case of spherical symmetry, the expression for the flux, it is nothing but ER, the radial component, ER multiplied by 4 pi into the variable radius R squared. So once again, I take two cases. In the first one, I consider R to be less than capital R, which implies I'm inside the uniformly charged sphere. Now in this case, if I consider this radius small r at which I am trying to find out over there the Gaussian surface, the electric field, what I need in this case is a Gaussian surface which is a concentric sphere, shell rather. Now as usual, if I compute the flux, we have already seen that this flux is going to be equal to the radial component of the electric field multiplied by 4 pi into small r square, which is a variable radius in this case. Now what about the charge enclosed? Now in this case the sphere is uniformly charged. Let's consider the volume density of charge as rho. So this is nothing but charge per unit of volume. So charge per unit of volume of this sphere is equal to rho. Then if I look at the charge enclosed by our Gaussian surface, it will be nothing but the charge in this part of the sphere. But that can be obtained by multiplying the density and the volume, which is becoming 4 by 3 pi into small r cube. So if I now replace the two expressions in the Gauss theorem, Gauss law, so if I look at Gauss's law, will imply then that the radial component ER into 4 pi r square should be the density multiplied by 4 by 3 pi r cube. This means therefore that the radial field is nothing but rho by 3 epsilon naught into r. So interestingly, it's proportional to the distance actually. Fine. In fact, by noticing this fact that the electric field must be radial. If it's positive charge, it must be radially outward. If it's negative charge, it must be radially inward. So by noting that, we can actually write down the electric field in a vector form, and that will take the form as rho into the position vector r with respect to the center of this sphere divided by 3 epsilon 0. Okay, this is the vector form of the electric field inside a uniformly charged sphere. This is important. What happens when you go outside? Well, either by using Gauss theorem directly or by using the shell theorem, we can notice in this case that when we go outside, the left hand side of the expression remains the same, but the charge is now the total charge. Okay, so we could write down therefore that the flux, which is the radial field, into 4 pi r square, it must be rho into 4 by 3 pi into capital R cube, because now I am dealing with the total charge of the sphere, though the Gaussian surface extends all the way outside, but the charge is only present on the sphere, and the result of which we have to take only this portion, and that will give us the electric field as rho by 3 epsilon naught into r cube upon r square. So it just falls as 1 by r square as it does for a point charge. In fact, we could write down this electric field in terms of the total charge over there, this total charge. If I take this as q, for example, then this q remains over there, while this 4 pi square goes down to the denominator on the right side, and therefore we shall actually end up getting, in terms of the total charge, simply as q by 4 pi epsilon 0 into r square. This is nothing but that of a point charge, electric field of a point charge. That means effectively that in this case also, for outside points, we can think of this sphere as if it were a point charge. That's the reason why, for example, the Coulomb's law is applicable for two spheres which are uniformly charged as well, because for each of them the other looks like a point charge from the outside actually. Fine. Now, as usual, if you look at the variation for the electric field, well, for inside points we can see that it varies in a linear manner like a straight line, so it should be just going like a straight line, but the moment we go outside it just falls as 1 by r square, so it just becomes 1 by r square, it becomes less and less, and this max value happens to be at the radius. Fine. This becomes the electric field variation for a uniformly charged sphere. Important result is for the interior points, we should keep that in mind. Fine. Next we consider the electric field of an infinitely long line charge. So basically in this case we consider that we have an infinitely long line charge like this. This is infinitely long, would have drawn for only a small part of it, and we are interested in finding the electric field of this long line charge at a point which is at a distance smaller from the line, like this. We shall assume that this line charge contains a charge per unit of length as lambda. This is the charge per unit of length. As a Gaussian surface in this case, we shall draw a coaxial cylinder. So a cylinder which has the same axis with the wire, and the radius is exactly the same as the distance we are trying to find out the electric field. So if I consider a Gaussian surface like this, which is, as I said, a coaxial cylinder over here, what we notice is that the electric field in this case by symmetry should be only radially outward from the line. It cannot have any component parallel to the line, for example. Okay, it has to have only one component which is radially outward. In fact, we can prove this, not very difficult actually. So if I now consider a certain patch over here which is over which I'm trying to which is try to compute the flux, and we notice that in this case the electric field and the area vector once again are in the same direction. So for this curved surface, for example, the electric field and the area vector are pointing in the same direction, as a result of which, if I look at the flux in this case, this total integral over the closed surface, I could break it up into two parts. One is the integral over the curved surface, curved portion, of E dot dA, and the other one is over the caps. Right? However, we notice that on the caps, for example, on this cap, for instance, the area vector is going to be this way, but the electric field is going to be that way, this right angle over there, and that implies the contribution to the flux from the caps is zero in fact. So what survives is only the contribution from the curved portion, and on the curved portion we find that because E and D are in same direction, this is nothing but turning out to be just the electric field, the radial component into dA. Again, utilizing the cylindrical symmetry, we can pull this E out of the integral because it must be same at that radius. And so what I end up getting is E into dA, which is asking us to simply add up the area of those little patches on the surface. And if I just add them up, I'm going to end up getting the curved surface area. So assuming the length of this shell cylinder to be L, we end up getting the area as 2 pi r into L. This is there for the left hand side of the Gaussian theorem, and this will be always the case whenever you consider the a cylindrical symmetry in fact. Now if I look at the charge enclosed by the Gauss's law, what we have the flux E into 2 pi r into L, it should be the charge enclosed. Now, the charge enclosed in this case is what? It is basically the charge point of length multiplied by the length. That is the charge which is inside the Gaussian surface. So this upon epsilon 0, L gets cancelled out, and that gives us the electric field as lambda by 2 pi epsilon naught into r. Fine. This becomes a for the electric field due to an infinitely long line charge, which we have seen already. I believe that this is how we can obtain this up from by using integration as well. Next, we consider what happens when we have an infinitely long cylindrical shell. Okay, this time what we have is actually a shell, a long cylinder which has no end, though I'm showing only part of it actually. The axis is somewhere in the middle. So this long, infinitely long shell of charge, it is charged only on the surface. This is shell, which implies an envelope. Right, this is an envelope over there. As usual, I mean, this is charged on the surface, which I am assuming the density as sigma per unit of area actually. So if I take the points which are inside the interior, like for example this one, I again consider a Gaussian surface which has this radius r and it is coaxial like this. Let us say the length is equal to L. As usual that we have seen earlier, in this case the Gauss theorem, Gauss law will reduce to, because we are taking a cylindrical symmetry, the left side of the flux calculation, that turns out to be nothing but the electric field on the surface of that Gaussian surface into 2 pi RL. Now in this case, if I consider the right side, the charge enclosed, it is nothing but 0. Because this is a shell and all the charges reside on the surface, only on this surface, as a result of which the charge that is enclosed in the surface is simply 0, and 2 pi RL can't be 0, as a result of which the electric field has to be 0 itself. Very similar to a solid, a spherical shell. Even for a cylindrical shell, the electric field is 0 inside, but providing that it is infinitely long and uniformly charged. Fine. As usual, if I go for the outside point, say for example I am over here, then I'm going to consider a Gaussian surface which has this much of radius, so coaxial, and the radius is equal to this r that we are looking at over here. Point over here is that again the left hand side is going to be the same. It will still be the same expression, which is E multiplied by 2 pi r into L, but the right side over here is a bit different. Right side is going to be now the charge on this portion of the cylinder only, which is intercepted by the Gaussian surface. However, the charge is only on the surface actually. Therefore, we should write down sigma multiplied by the curved surface area, which is nothing but 2 pi into capital R into the length, because it's a surface area, divided by the epsilon naught, and that gives us once again the electric field as sigma by epsilon 0 into capital R upon small r. Fine. So the electric field once again turns out as 1 by r actually. It's very similar to the charge because of a line. In fact, if I wanted to express this in terms of the line charge point of length, then you can see easily that if I take this length of this cylinder, the sigma, the charge which is present is sigma multiplied by the area, which is 2 pi r into L, but I also want to write down this in terms of the linear charge density, lambda, so it should be lambda into L as well. But that gives us that sigma into 2 pi r is the corresponding linear density lambda. So I can use it over here. I could multiply and divide by 2 pi, and this gives us simply lambda by 2 pi epsilon 0 into r, which is what the electric field is for a line charge as well. One particular thing that you should notice over here, and we also saw that in case of a uniformly charged shell, in fact, that there was an abrupt change in the electric field as we go from inside to the outside over there. You could see there's a sudden abrupt change as we go from the interior point to the outside point. This also happens in this case when we have this long cylindrical shell. There also there's an abrupt change. Inside the electric field is 0. The moment I reach the surface, it jumps to a certain value and then falls down abruptly as 1 by r. This is, in general, we shall see a very general property of the electric field, that whenever you encounter a surface charge density, then the electric field becomes discontinuous. In fact, it's a normal component which is becoming discontinuous actually, right? So that's we have for the cylindrical symmetry. Next we consider, well, let's take a uniform cylinder, which is kind of a generalization over there of the previous one. We can again in this case consider a uniform cylinder, and this time, however, the charge is filled sorry, entirely inside the cylinder. So it is filled all inside, solid. Now in this case, if I want to find out the electric field, once again let us consider a point which is inside, like for example over here. Then as a Gaussian surface, I shall consider a cylindrical, a coaxial cylinder with the same radius, and suppose the length is L. If I compute the flux as usual for a cylindrical symmetry, it will become E into 2 pi r into L. On the right side, it should be the total charge which is enclosed within. Now this time it's a volume density of charge. We shall assume that the total volume density is rho, which implies that this is the volume charge per unit of volume over there. So in terms of this, the total charge enclosed is going to be the density multiplied by the volume, which is pi into r square into L. Divide this by epsilon naught, and pi gets cancelled out. This comes out to be density rho by 2 epsilon 0 into r. Fine. So it once again is varying in a linear fashion, but this time it is going to be the distance from the axis actually. R is in this case the distance from the axis of the cylinder. Once again, if I go to the outside region, R becomes more than R. For example, if I go over here, Then as my Gaussian surface, I'm going to consider a cylinder once again, but this time the radius is equal to this value r, and again I can take the length to be simply L itself. This time if you compute the flux, it is still E into 2 pi r into L, but the charge enclosed now is actually only the solid cylindrical part, the outer portion or these parts of the Gaussian region that don't have any charge over it. So the only charge is inside the cylinder. Therefore you should write down rho into pi capital R square into L by epsilon naught. So what happens is the electric field E turns out to be rho upon 2 epsilon naught capital R square upon small r, right? This is electric field which is going to be there for outside points. Once again it varies as 1 by r. So that's a usual case. For a cylindrical symmetry, the field outside varies as 1 by r, right? Next we consider the electric field of an infinitely large sheet of charge. This is a planar symmetry that we have an example of. We shall imagine in this case that we have a very large plane, is practically infinitely large, and this is charged with some charge density which is going to be sigma, that is charge per unit of area. This entire sheet is charged over there, right? Now in the Gaussian surface over here, we are going to consider a pillbox. Like we could take a cylinder, or we could just take up a cuboidal box as well. This cuboidal box is going to be straddling it. Some part is on this side, some part is on the other side, and the length of the cylindrical box, the cuboidal box, is exactly equal to the distance x at which I'm trying to find the electric field from the sheet over there. Fine. Let's say the area of this cross section is capital A. Over here we notice that the electric field of the sheet is going to be normal, either this way or that way. Fine. If it's positively charged, it's going to be pointing outwards, negative will be pointing inwards. Now the flux will not be getting any contribution from these faces over there which are on this side. They will not have any contribution from this face. The only contribution comes from the front face over here and the back face over there. As a result of which, if I look at the flux of the electric field, it is simply E into A times 2. One for the outer face, one for the inside face, or the face on behind actually. And what about the right hand side? The right hand side gives us the total charge enclosed, which is actually the charge straddled by this cylinder over here, this box over here. So that will be nothing but sigma into the area itself upon epsilon naught, and that gives us over here the electric field as sigma by 2 epsilon 0. If you look at the direction, it is sigma by 2 epsilon 0 on this side over here, but behind it will just go on the opposite side. The magnitude would remain the same, but the direction changes abruptly as you go from one side to the other side. That is what we saw when I said earlier that the normal component of electric field that becomes discontinuous, right? As you could see, if I just try to look at the electric field in this case, it is simply a constant value on this side and the other side, same value, but direction becomes abruptly different. Okay. Next we consider the electric field of a very large, infinitely large technically, slab of charge. So this is kind of a thick slab like this. So this dimension over here is finite, the thickness, but every other dimension is infinite. In this case, if I consider the plane that goes through the entire middle, a symmetrical plane over there, electric field are going to be symmetrical above this line in fact. So this is a line of symmetry over here. Look from the side, if I see a slab like this. I'm looking along this direction and I see the slab is going to be something like this, a thick slab. We are interested in finding the electric field because of thick slab, both inside the slab and outside it over there. So as usual, we have this particular plane of symmetry, and we're going to find out the electric field at distances x from this particular plane. First of all, when I'm inside this, say I just take a distance x, I'm looking at the electric field at this point over there. Then what I do is I take a Gaussian surface as usual that we have taken in the last case, a box which straddles it. I'm showing the side view in this case. The box will be actually something like, in this case, straddling it like this one. What I am showing in this case, the side view over there. So the area is actually this face and the length is twice x. Electric field will be pointing this way over here, assuming positive, and this way over here, assuming positive again. For negative, it will be pointing in the opposite direction. So if I look at the flux in this case, what I end up getting is again twice E into A. E into A for both the right and the left face, but there is no other contribution from the surrounding faces actually. What about the charge enclosed? The charge enclosed in this case is going to be density of the charge, which I'm assuming that this slab is filled with, a volume density of rho entirely. Then the volume is going to be the area into the width, which is 2x divided by epsilon naught. This gives the electric field as rho into x upon epsilon 0. So electric field varies linearly as long as we are inside the slab. Fine. What happens in outside? If I go outside, this is for the region where mod x is less than the thickness, half the thickness, d by 2, assuming the total thickness in this case to be d of the slab. If I'm going for outside points over there, once again this area that I'm going to take over here is going to be coming out of the slab like this. This is now the length of the cuboid. The area remains the same. So this time if I compute the flux, that will be still twice E into A. However, the total charge enclosed is going to be the one which is only in this portion of the slab, and therefore by applying the Gauss law, what I can get is over here twice EA is equal to the charge density rho multiplied with the volume, which is A into the total thickness d by epsilon naught, which gives us the electric field as rho by 2 epsilon 0 into d, which is a constant field actually. So if I look at the variation for the electric field both inside and outside, then I find that interior points varies in a linear manner till we reach the surface. Then it just becomes a constant on both the sides. This is becoming, in this case, the variation for the electric field with respect to the distance from the middle plane actually. In this case, our symmetry plane is the mid plane, and we are looking at the distance from that particular mid plane, right? So these are a few applications of the Gauss theorem, Gauss law, in order to obtain the electric field. I hope it is going to be useful. You will find it useful. Thank you for your attention, and till the next video, that's all.